Boa tarde, pessoal. O pessoal que está online consegue me ouvir também? Sim, apareceu o joinha. Tem aqui 32 pessoas online, e a sala cheia também. A gente combinou aqui de fazer uma introdução em português, e depois o professor vai fazer a apresentação dele em inglês. Vocês podem depois fazer perguntas também, em português ou em inglês, que a gente vai ajudar, se for necessário. Bom, então, muito bem-vindos, todos e todas que vieram aqui participar dessa atividade junto com a gente. A Unicamp, a gente tem uma parceria já bem consolidada com a North China Electric Power University, que é a universidade de onde vem o professor Yongli. E também a gente tem uma cooperação que já consolidada e crescente com a Xamano Energy, que é representada pela Cláudia. Esse evento faz parte desse esforço de cooperação. Hoje também a gente tem participando aqui do evento com a gente a professora Marlise, que está aqui representando a nossa pró-reitora de pesquisa, e temos também a professora Ana Elisa, que é diretora do nosso Instituto Confúcios aqui na Unicamp, a diretora brasileira, né? Porque o Instituto Confúcios também tem um diretor chinês, que é o professor Gao. Então, essa é só uma pequena parte da grande cooperação que a Unicamp está construindo com a China. Então, por exemplo, ter Instituto Confúcios dentro de uma universidade no mundo inteiro é um privilégio de poucas universidades. A Unicamp tem esse instituto, depois a Ana vai falar um pouquinho sobre o Instituto Confúcios para vocês também. E a professora vai falar um pouquinho também, representando a nossa pró-reitora. Muito bem. O que a gente vai ter hoje é uma palestra do professor Yongli. Eu vou falar um pouquinho aqui para vocês sobre o currículo dele. Então, o professor Yongli ele trabalhou na Universidade de Limerick, na Irlanda, e também no Instituto de Tecnologia, esse nome é alemão, Karlsruhe, sei lá como é. Alguém aí fala alemão? Que é na Alemanha, né? E após ele ter terminado o seu doutorado, que foi na França, em Caen, na Normandia. Atualmente, ela é professor titular da NCEPO, que é a North China Electric Power University. A Unicamp, como falei, tem uma parceria importante com a NCEPO. Agora, por exemplo, a gente está mandando uma comitiva de 10 pesquisadores nossos para o que eles chamam de acampamento de verão para a formação de jovens lideranças em energias renováveis. No ano passado, também, a gente mandou 10 pesquisadores da Unicamp para esse evento na China. É uma parceria entre a Unicamp e a NCEPO. A Unicamp financia a viagem, passagens, e a NCEPO financia hospedagem, alimentação, toda a parte interna na China. É um evento riquíssimo, com a agenda acadêmica, com aulas, palestras, também uma agenda cultural, com aula de Kung Fu e de mandarim, e também uma agenda tecnológica, com visitas às principais empresas chinesas nessa área de energias e transição energética. E também tem uma agenda gastronômica, o pessoal vai comer o que tem de melhor na China. É fantástico, os nossos alunos que já foram, tem alguns aqui, adoraram, e agora estamos mandando mais 10. A ideia é todo ano a gente enviar 10 pesquisadores nossos. Continuando, então ele é professor titular na NCEPO. Ele foi um pesquisador que fez carreira na Europa por muitos anos e foi repatriado pelo governo chinês. Ele é diretor do Instituto de Tecnologia de Energia Limpa, da NCEPO. Coordena os maiores projetos na China nessas temáticas de transição energética. Sua principal área de pesquisa inclui armazenamento de energia eletroquímica, a eletrólise da água e tecnologia de microprocessos. Publicou mais de 50 artigos em revistas de alto impacto, possui cerca de 40 patentes concedidas, atuou como pesquisador principal em mais de 30 projetos de pesquisa. Também ocupa o cargo de presidente do Comitê Acadêmico do Laboratório de Tecnologia de Armazenamento de Energia com Bateria de Sódio, na província de Shanxi, na China. E, além de ser membro do Conselho Editorial da revista Energy Storage and Savings. Então, é um privilégio para a gente poder ter uma palestra hoje do professor Yongli. Antes de convidar o professor, eu vou convidar a professora Marlise para falar umas palavrinhas pela pró-reitoria, e também a Ana, vem aqui, Ana, falar uma palavrinha para vocês sobre o Instituto Confúcio.
Boa tarde a todos e todas, é um prazer estar com todos aqui. Fiz até uma cola para entender, porque eu não sou da área, mas para entender a importância, né? Primeiro eu queria agradecer o convite do professor Luiz Carlos. Com a fala dele eu tive uma dimensão dessa parceria entre as universidades e a parte da indústria também, né? Então, eu espero que todos possam desfrutar e apreciar essas pesquisas de ponta, que são para enfrentar as questões críticas de energia renovável, transformação energética. Então, essa colaboração e parceria entre as nossas instituições, né, e a indústria, lideradas por grandes pesquisadores e empreendedores, né, são fundamentais para a criação de soluções aplicáveis no mundo. Então, se a gente pensar, eu sou da área da saúde, mas se dizermos que, no caso, a saúde no nosso planeta, ela depende dessas soluções sustentáveis, como as que estão sendo discutidas hoje, com esse evento, na palestra do professor Yongli, e todas essas colaborações já implementadas e continuando. Então, parabenizo o professor Luiz e agradeço a oportunidade de estar aqui.
Bom, boa tarde para todas e todos. É um prazer enorme estar aqui, em especial para representar o Instituto Confúcio, do lado brasileiro, aqui na Unicamp. Esse ano, em abril, nós fizemos 10 anos nessa parceria, mas, infelizmente, ela ainda é um pouco tímida dentro da universidade, né? Não sei se vocês sabem, o Instituto Confúcio tem um lugar físico aqui dentro da Unicamp, que fica ali na Biblioteca César Lattes, então está aberto para que vocês possam visitar. Nós estamos, inclusive, agora com as vagas para os nossos cursos abertas, são cursos de música, de mandarim, de dança, então convido vocês também a se aventurarem no nosso site e a verem o que há de disponível. E a gente está com um projeto de ampliar e fortalecer várias parcerias, e eu fico muito feliz que isso aconteça aqui, né? O professor Luiz, ele é uma pessoa extremamente agregadora, e ele conhece muita gente, e isso também é super importante para esse projeto de ampliação e conhecimento e divulgação do Instituto, nessa relação de troca, né, cultural, de conhecimento, de tecnologia, né? O professor Gao também, que é o diretor pela parte chinesa, a gente estava comentando, ele é um centro de informações, então se vocês também tiverem interesses em outras instituições, em outras áreas do conhecimento, nós lá pelo Instituto estamos à disposição para fazer também essa ponte, e fico muito feliz que a gente tenha colegas que estão estreitando essas oportunidades, trazendo professores como o professor Yongli aqui, para fazer a sua palestra, a sua troca junto conosco. Então, muitíssimo obrigada e parabéns pelo evento e pela organização, viu, Luiz?
Eu queria dizer também, pessoal, que essa relação, ela, aqui na Unicamp, é coordenada pela Diretoria Executiva de Relações Internacionais, né, que é o nosso escritório de Relações Internacionais da Unicamp. O professor Rafael hoje não pôde vir aqui, que é o diretor, mas ele pediu para mandar um oi para vocês aí, e essas relações internacionais da Unicamp todas passam pela DERE. Essa comitiva, por exemplo, é financiada através de recursos dessa diretoria. Então, a Unicamp está cada vez mais buscando aumentar a internacionalização, né, e as cooperações. E hoje em dia, as maiores oportunidades que a gente tem de cooperação são com a China, só para falar um pouquinho disso também. Professor Yongli, thank you very much. So we're very happy to receive you here.
Thank you.
In our School of Electrical and Computer Engineering. And now we'll have time for a speech.
Yeah.
If you can stay close
Yeah.
here.
Okay.
Yeah.
Yeah.
Also the virtual audience.
Okay. I try to check here. Okay. Yeah. So thank you very much for the introduction and the welcome speech. Even I didn't understand much, but I feel very good. Thank you very much. Yeah. And especially thank you for the invitation. Yeah, it's my honor to be here to give the presentation. Yeah. So today, the presentation here, the title is Hydrogen Energy Development and Hydrogen Production by Water Electrolysis. My name is Yongli Li from North China Electric Power University. So my institute named Institute for Clean Energy Technology. Thank you. Yeah. So here, I will go through the three sectors. The first one is University and Institute introduction. Yeah. So our university was established in 1958. The name is North China Electric Power University. And because in China, we have different classifications for the universities. For example, I think before, some years ago, the most important, it was 211. That means 21st century, 100 universities. In China, we select about 100 universities to be in this ranking. Our university was one of this. And our university was specialized for the power engineering, electric engineering, and the new energy, etc. Yeah. But today, I think since about 5 to 10 years ago, we changed to another classification we called double first class. That means world-class university and world-class discipline. So our university was also in the list. That means the Chinese government support our university for developing on this discipline. Yeah. So our university belongs to Ministry of Education in China, but a little bit different from the other ministry-owned universities is we have a council here. With spot on. Later point, yes. We have a council for the university, and this council list member is all the large Chinese electric groups. For example, State Grid, China Southern Power Grid. I think these two are the largest in China. And also we have Datang, Huadian, and China Energy Investment and CTG, etc. I think all these big electric groups, they represent, I think, more than 80% of electric power in China. Yes. So it's a very special university in China, very close related to electric industry. And our university have 4 national level research platform and about 36 provincial and ministry platform. Yeah, so these slides I copied from our international office. For the first one, yeah, we have a chemical engineering, energy for fuels, we have a good rankings. And here are from the international office. But for me, the most interesting part is the last one. You know, in China, we have a very important exam. It's called entrance exam for universities. I think that's the most important exam in China because this exam will select the good students for going to universities. Yeah, then you can get good university or normal university only by this exam. Okay, what happened? Electric problem, yeah. All right. Like, this one.
I think you can continue.
Okay.
In a few minutes, you can restart the.
Okay. Yeah. Yes. No problem. Then I watch here. Yes. Yes. Sorry, I have to go here. Yeah. So because our university, we have selections the university by this entrance exam, because our discipline is good. Chinese government pay attention to our discipline, and all the economically development in China is a major as in this discipline. So that's why the students, they try to come to our university And that's why we can select the good students. So I'm very proud of the students. Yeah. And here, you don't see it, sorry. But here, this is the international collaboration partners in the world. We have partners in Europe, in America, in Japan, South Korea, Australia, and also in Brazil. In Brazil, at the moment, we have only 1 point. It's Unicamp is here. Yeah, it's our international collaboration partners. Yeah. So here it is my institute. Our institute was founded in September 2022. I think now it's 4 years ago. Yeah. This institute, we have a lot of researchers, about 35 researchers in the institute. So the research topic, we have 2 parts, mainly divided by 2 parts. The first one is about, okay, it comes, good. So in the institute, we have 2 research directions. The first one is related to hydrogen, second one related to the batteries. For the hydrogen part, we try to develop a water electrolyzer systems. And our colleague working on the catalyst, and myself, I'm working on the structure design based on heat transfer and mass transfer. And also we develop these corrosion resistance coatings for the plate. And also when we produce the hydrogen, the next problem is how to store the hydrogen and how to use the storage for transport. So in our institute, we try to develop the microreactor technology, and we use this microreactor to convert the hydrogen to fuels, for example, SAF. Yeah. And another part is we're working on the energy materials, for example, solid-state battery and the sodium-ion battery. The sodium-state battery, we work on it. The reason is we try to make the battery safe, because in China at the moment, we have a lot of electric cars, and also we have a high demand for the energy storage by the batteries. I think due to the development of the electric cars in China in the last few years, so we have a good technology accumulation at the moment for the battery itself. And also we have a few good companies, yeah. But nowadays, we try to use the same battery for the energy storage. Then we have problem, because the energy density from the energy storage is much more higher than for the power engine energy. No. So then we have a problem is the safety. Because I don't know in Brazil if it's common to see the energy storage this in the big container. Because in China we have more and more. I think in the largest I have met, it was gigawatt. It's gigawatt energy storage with batteries. So inside, to save the space, we try to put high energy density inside. So all the battery cells, they one by one connected. Yeah, that means we almost have no space even for the fire protections. That everything is all connected. Inside, then they have to protect from the dust. Then the system will be closed. Yeah. So in such system in gigawatt, you can imagine if one battery get burned, then the whole system will be in danger. Yeah. The battery at the moment, for example, we have always the solvent is the organic solvent. So organic solvent gets easily burned. So we try to reduce the organic solvent, the application, then we try to use solid state battery. So we believe the full solid battery will be resistant to the fire. So, but at the moment, the solid state battery is, the first is too expensive, and the second is, for example, the lifetime is too short. For the normal lithium-ion battery in China, we can get almost 10,000 times cycling. Yeah, but for the solid state battery, for full solid state battery, we can get only 100, maybe 200 times. It's too less. Yeah, so that's the problem. That's why we're working on it. The second is we're working for sodium-ion battery. For sodium-ion, oh, from this. Okay, I continue here. Yeah, yeah. For the sodium-ion batteries, why in China we developed this technology is because we have increased demands for the batteries, lithium batteries. Then we don't have enough the mine storage for the lithium. Then we try to shift to sodium, and we can solve the problem from the mine. Yes, yeah. So in my group, we also work for sodium-ion batteries. Yes, and also supercapacities. And also, because we have increased application with batteries, a lot of batteries will get retired in the next few years. But for these batteries, the first they considered as a dangerous waste. You cannot throw it away. You have to take it back. Second is we try to reuse it as a raw material to come back to the whole life cycle again. Yeah. So what we do is, but normally I think here we have one thermal method and second is acid method. We can all recover the materials, but either they consume too much energy or they can create pollution issues. Yeah. So this try at the moment we work with a German company. We try to use all physical method. With the physical method, we separate all the elements. We don't try to separate all the elements one by one, purity, but we try to get them with a package. Then with this package, whole package go back through to the raw material. At the moment, we got some improvement, yeah. And also for the last one, because this development is still for the basic research, but for the whole this managed thermal energy storage system, the most important is the battery thermal management to keep it safe. So we developed some immersion cooling system, phase change materials, heat pipe cooling for keep the temperature of the whole system. So that's basically the research direction in my institute. Yeah, this is a group member in my group. Yeah. Yes, I just forgot. Maybe I make a brief introduction about myself because I did my master's degree in France. Yeah, University of Savoie. Then I did. I worked in University of Lorraine in France. It's the Institut National Polytechnique de Lorraine. The LANSIC is engineering school for chemical engineering. When I finished there, then I went to University of Gand and University of Rouen for joint a program for PhD. When I finished, I got a Marie Curie fellowship. And with this fellowship, I went to University of Limerick in Ireland. So in Ireland, I worked a few months. Then with second month, I've come back to Karlsruhe Institute of Technology in Germany. Yeah. Then there I stayed for 1 more years. After here, I come back to INSA Toulouse, Institut National de Sciences Appliquées de Toulouse. There I finished this Marie Curie fellowship. When I finished, I came back again to Karlsruhe Institute of Technology. I stayed there for a few years. So in 2017, I came back to China and joined this university. Yeah. I founded this institute in 2021, and in last year, 2024, I founded a new department. It's called Department of Energy Chemistry. Yeah. So that's why I have some partners international partners, because my last experience really traveled, a lot. So, this is my institute. We got some publication and got national awards. This is some papers. And here we have some national project, industry project selected. Yeah. They don't work. Sorry. Yes. Yeah, I would like to present one of our current project. So this project is a National Key Research Development Program. So this program is mainly for hydrogen production. I think we've got funded in 2022 and until 2026. It will last for 4 years. The total funding is 140 million. Yeah. In this project, we have 5 sections. The first is about MEA, the membrane electrode. The second is about the PTL, porous transport layer, and bipolar plate. Then here we have assemblies. Then here for industry, for the stack. Then the last one is for this demonstrations. Yeah, here the second part, I take responsibility for the second part. And then we have a few partners in China. I think these partners in China will represent the best level in China for these hydrogen productions by PEM system. Yeah. So let's we go about for the hydrogen energy development. This is also a new topic for me. Before I didn't prepare some slides for this. Sorry. For example, for the traditional energy, we have challenges. For example, the oil, coal, gas put together will take almost 80% for the global energy consumption. So that means we have some challenges from the fossil fuels for the 3 sections. The first time, we have limited and unevenly distributed. For example, in China, we have a lot of coal, but we don't have many oil and gas. Yeah. So that means our industry for development, we need to focus how to make use of the coal. That's, I think in the last 20 years, a lot of Chinese researchers working on coal development, try to convert the coal to the gas, etc. And also, for example, when we have an increased demand for this fossil fuel, then we need to find this in somewhere else, for example, complex area like deep seas, etc. The second is about the climate ecological impact. For example, at the moment, fossil energy, they contribute 76% of the global CO2 emissions. And also they will create pollution to the air, ocean, and land. The last one, we also, I think today we have a big problem because of this. And because the distribution of the energy is not exactly the same as distribution with the populations. So we have the problem of geopolitical conflicts. And also, because also the supply chain, international supply chain is not stable. So in China, we have a lot of coal and scarce in oil and gases. But for example, in 2023, if we check for this energy consumption in China, we will see for the non-fossil energy, we have only 16%. But 16, maybe you read in the news, you can check in China, we have more installed power, but in reality, a lot of power, they are not being used. Because yes, we installed this renewable energy power, but the grid, they don't like this kind of energy, so they don't use it. So in reality, we have only 16% from the non-fossil energy. But from this, we have a hydropower, also nuclear power. For PV and for the wind energy, we have about 4%. So it's a really small percentage. For example, over the years, we believe the wind energy, solar energy in China, the system consumption will be much increased. And for example, here by the September 2024, the total installed capacity is about more than 1,000 gigawatt. And here, the breakdown, we can see the hydropower 430, wind power 480, solar power 770. But in China, the hydropower we almost used, we finished. So the development will be all realized here. I think, and also because China, we have a commitment for the climate change. We try to get peak carbon emission before 2030 and achieve carbon neutrality before 2060. Our president announced it before the world, then we have to finish it. So energy power section accounts for the largest portion of carbon emission. For example, here, it means electricity. Here is emission of CO2 per year. The electricity have 40, here is 100 million ton per year. So electricity have the largest portion. According to this report, the 80% of the reduction in carbon emission will coming from the new energy, in energy transition, like a PV system, wind energy, and the 20% will come from energy saving over the existing process. Then we go to the hydrogen energy, because the hydrogen energy in China now is a very hot topic because they have a good advantage as low carbon emission, high efficiency, etc. Before, in China, we also produce a lot of hydrogen, but the hydrogen mainly used as chemicals, as raw materials, because we have heavy industry, chemical industry. And I think from now on, as energy carrier, the hydrogen will give more importance. So as energy carrier, the percentage will be increased, and also as raw material will be go down. That's a trend tendency in China. So hydrogen, why we use hydrogen in the electric power system is because hydrogen is a good energy storage media. But we have different this energy storage method. For example, as the batteries and also as compressed airs. We have different sections in China. But why we use hydrogen? For example, when we compare to battery, at the moment in China, we have most of energy storage is with batteries. But why we don't use batteries? Because the energy density of battery is too low. For example, when we increase the capacity, then we need develop a lot of batteries. I think it's not a sustainable way for using battery for energy storage. But the battery itself, their good advantage is where they are very flexible. So we can use hydrogen as a storage media, then we combine with batteries that will work. I think this concept at the moment, we also, for the electric cars, with the fuel cell cars, they still use a lot of batteries, try to compensate, they have their own advantage, yes. And also, a lot of research working on compressed air. This is completely physics. But for these systems, they need the natural caves. Yeah, if we don't have it to build the caves, it's also very expensive. Yeah. So I think the main economics in the world at the moment, they all making plan for the hydrogen energies. Yeah. In China, I think we at the moment, we try to, this in Europe, sorry. In Europe, they try to making the plan. The aim is to reduce the CO2 emission. In my opinion, the Europe is take responsibility for the human beings. Yeah. So that's why they have the CO2 emissions. They try to make the policy. I think they are the most active part in the world. They try to do this. Yeah. And also, I think due to the political reasons, for example, in Germany at the moment, they abandoned nuclear already. At the moment, they have a problem to get the gas from Russia. Then they have to use hydrogen. So then they need to develop this technique too. Yes. For the Brazil, I found this by internet. I don't know if it's true or not. Yeah, because I think this name is 2050 Energy Plan Brazil. Yeah, I think inside I found it. I think your aim is first is to reduce CO2 emissions. Second is hydrogen export for economics. But in my opinion, I heard here you have 85% of power energy coming from renewable energy. So I think CO2 emission is not a problem for you. So, but I think maybe the hydrogen export to China, for example, is a good economic way. Yeah, yes. So I think different countries have different thinking for the hydrogen energy. Yeah, for example, for Korea, for this country, because Korea is very good for the car industry. The country is small, but the car is very powerful. But at the moment, if they want to keep the advantage of the car industry, they have to develop fuel cells. They have to develop hydrogen systems. Sorry? Yes, come back. Yeah. So I think the purpose for them is for car industries, in my opinion, yes. And for America, they try to get more reliability, get a variety of power supply to make it safe. In my opinion, it's this. And I think for Japan, for example, they don't have much resources. So for very early stage, they already started looking for hydrogen energy. I think it's also for safety reasons. In China, I think we also made a lot of planning in recent years. But in my opinion, we have two major reasons. The first reason is we try to take responsibility, like the one I said, the 2030 and 2060 aims. Yeah. The second is because we try to keep safety. Because in China, for example, we have a lot of coals, but the coal cannot be used directly for the cars. Yeah. For example, if we have something happened, we need to have the energy supply inside the country ourselves. So for example, if we develop these electric cars, then these cars, we can use electricity produced by the coal. That means we are independent from the oil that keep the country safe. I think this is also very important for us. If we develop like this, we can, even we don't have oil, we can still keep longer running daily life with coal. Yeah. And the last one is for economic. I think a few years ago, in the world, you can find the cars from Japan, cars from Europe, from America, but seldom you can find the Chinese car. But today it changed because like BYD, I saw it also here. The reason is BYD, basically, it was a battery company. Yeah, that means they have very good for the battery electric cars. So economically, it's also good. They put our car companies to the front of the world. Yeah, so I think the three major concerns in China. Yeah. Then we come to this hydrogen demand. For example, 2023, in the world, they have 97 million tons. Yeah, only less than 1 million tons by green hydrogen. Yeah. And China nowadays, we have hydrogen production capacity of 40% of the global productions. And for the electrolyzer manufacturing capacity, we represent 60% of the global capacity. That's really high. Yeah. And we can expect by 2030, the green hydrogen production can reach 49 million tons per year. So that's really a huge market for the green energy. Yeah. according to IEA report, yeah, that global hydrogen demand will reach 520 million tons by 2050. And if China accounts for 30%, so that means 150 million tons. Among them, 109 million tons of hydrogen will be used for power generation. That means this will be a revolution for Chinese energy structures. Yeah, for the complete hydrogen energy development, at the moment, still on the initial stage and demonstration. For example, for the productions, we have water electrolysis for hydrogen production. This part, we try to develop this in our institute. I think also many universities in the world. And also, we have hydrogen production from fossil fuels and chemical raw material, hydrogen production, etc. At the moment, most of the production of hydrogen is coming from fossil cells. It's not from water electrolysis. Yeah. And then we have a storage and transportation problem. For example, nowadays we can store it in liquid hydrogen, but the problem is this hydrogen, if you want to liquefy hydrogen, you have to, except from pressure, you need to go to low temperature. So that makes things more complicated. And also we can use high pressure. Yeah, this is very common in China at the moment. And also solid state storage and other method. Yeah. And also transport, I didn't list it here. I think for me, most interesting is how to use it, the utilization. For example, for industry use as before, for example, as raw materials, for chemicals, and also for electric generations. For electricity generations, we have basically two parts. First, we use for fuel cells, and also we can use combustion. Yeah, we can combust only hydrogen, or we can put hydrogen inside something else. Yeah. But here, I think we also have a problem because the hydrogen can create embrittles of the metals. Yes. And also, we have the transportation. The transportation also is a huge part of the consumption of hydrogen in future. And also, if we have this power generated by the hydrogens, and we can use the waste for heating, yeah, as we are doing for the power plants at the moment. Yeah. In the whole world, the hydrogen energy industry is still in the initial and demonstration stage. Yeah, it's not really industrialized. For example, at the moment, for the hydrogen, we can see the electrolysis of the water only present a small part. Most are from the coal, natural gas, and the byproduct. Yes, and here, for example, car-based hydrogen production, nitrogen-based hydrogen production, and the insular byproduct represent 80%, 50%, or 5%. That means from water electrolyzer, almost zero. Now the percentage is still too low. Yeah. Yeah. From this map, we can see within the years, the hydrogen production cost will be much reduced. Yeah. By 2060, it will be reached 10. Yeah. So, and if this is true, then we can count by 2060, this development of the potential, for example, by water electrolyzer can reach 100 to 180 million tons per year. Yeah. At the moment, we have only this, and not the moment, it's 2030. Yeah. And for the CO2 emission reduction potential, by 2060, we can get 1.6 billion tons per year. Yeah, I hope we can reach this in the end, yes, by using hydrogen. Yeah. Yeah, for the next, I will try to go to the water electrolyzer part. Yeah. The green hydrogen, yeah. Green hydrogen means when we produce hydrogen from, for example, from water electrolyzers, also from biomass, also too. Yeah. But in our group, we mostly use water electrolyzers. Yeah. For the water electrolyzers, mainly at the moment, we have 4 different parts, 4 different kinds. For example, first one, alkaline. Alkaline system is the most mature technology at the moment. In my opinion, this technology is very good and also has a long history. I remember I heard it somewhere at the beginning. This technology was developed at the beginning was for the submarine, because for the submarine in the enclosed space, they try to produce hydrogen for the humans. Yeah, then they use this technology nowadays for production hydrogen. It also works very well. Yeah, here. The cost is cheap because this said for the alkaline environment, we can use cheap catalyst. Yeah, and also the temperature 60 to 90 degrees also okay. Yeah, but we have a problem is electric load. electrical load is really limited. The reason is because in this system, we use a porous separators. So that means we have a diaphragm in the system. And this diaphragm is porous. Then we have a problem because we have this hydrogen at this side, oxygen at this side. Then the hydrogen will try to diffuse through the pores to the oxygen part. Yeah. Then we easily get the mix. That's why this technology cannot produce real high purity hydrogen because of these reasons. And also, if we have a very good electric load, for example, on the side, we have a very good these reactions, electrocatalytic reaction for produce hydrogen, oxygen. If the speed is very fast, then the diffusion rate compared to this to the reaction is very slow. So that means this diffusion rate is constant. For example, if you have a high rate of production of oxygen, you have a small amount of hydrogen get inside, it is diluted, so it is very safe. But if we have a low load of electricity, then the reaction is very slow. We have a small amount of oxygen produced. At this time, you have hydrogen will get mixed with oxygen, then it becomes dangerous. Yeah. So that's why for this system, we cannot working for low range of the electricity load. Yes. And also, for example, because of these reasons, then we have this temperature will keep in this state, and also because we use this electrolyte, we use this CaOH. Yeah, with this electrolyte, we need to we have a higher ohmic resistance, and also because the system is not compact as PMWE, for example, so they have a long distance of the diffusion. Yeah, that's why we have a higher power consumption. For example, get a 4.5 to 5.5. Yeah, so in this system, it's a very mature technology, but we have problem. The main problem is hydrogen purity, impurity, and also the electric load. And also today, we try to produce hydrogen directly from the electrolyzers to put it in high pressure. Because we have a porous media, then if we increase the pressure of hydrogen, then you will increase the flux of the hydrogen to oxygen part. So that means the ALK system is not suitable for high pressure operation for today. Then people come to the second is PEM system. That means proton exchange membrane. The most important part is they replace the proton exchange membrane for this diaphragm, because this membrane is dense membrane, so they can separate oxygen from hydrogen. So we are very safe in system, and because the system is very compact, so we have a low ohmic resistance. That's why we have a lower this consumption of the energy. Yeah, and also because we have a good isolation from hydrogen to oxygen, that's why we can have very low load. For example, we can reach 10% and until 160%. And also the system we can sustain to high pressure. For example, today we can reach 70 megapascal in the system. Yeah. Okay, so, but the main problem for PMWE is too expensive. The reason is because for the anode side, firstly, we have acid environment. Sometimes we can reach pH equal to 2, the high acid environment. Then we have oxygen produced, so it's a high oxic environment. Then also here, we have, for example, if before, for fuel cells, we can use carbon materials. But in this environment, this carbon material will be oxidized to CO2 immediately. So here we have to use titanium. But if we use titanium, the price is very high. Yeah, and even titanium cannot resist for long. Then we need to put valuable coatings. For example, we use platinum. Yeah, this makes the whole system more complicated. Yeah, so then afterwards, most of the people working on PMWE is try to reduce the cost. Yeah, then for the AMWE is it's very similar to PEM system, yeah, from the structures, because here they use anion exchange membrane. But the most different is here, instead of use water, then they use the alkaline solutions. And this solution has OH ions, they can attack this membrane. They attack the membrane, the lifetime of anion exchange membrane at the moment is lifetime is very short. So it limits the complete use of the system. And also, the current is limited. Here it's rate 1 to 2. In my opinion, it's less than 1 at the moment. Yeah, it's difficult to reach a high current density. Yeah, but nowadays it's still in R&D demonstration. And the last one, SOEC. SOEC, in my opinion, is a good technique, but the problem is they need to working on high temperature. For example, we have like nuclear plants, we have the waste power, it's good to use it. But if you use something heating to get this temperature, to use SOEC, it's a have a problem. Because the temperature is very high, so we have less requirement for the catalyst. Yeah, because the kinetics itself is very fast. And also SOEC and SOFC, they can use both sides with one system. Yeah, and also good thing with this is SOEC can work with CO2. They can convert CO2 to CO. For example, we input CO2 and water together. In the end, we can directly get syngas. It's also a good advantage. But because the temperature is too high, the material in the whole system has a higher requirement for stability. So that's why this technology at the moment is also in demonstration, not really industrialized. Yeah, yeah, for this is for the, yeah, this is one by one that I already talked just now. But here, the good thing is this system can work for up to 50 years. The lifetime is long. They have a disadvantage, but they also have advantage. Yeah. At the moment, for example, in our project, we try to use PEM system because they have more flexible to the load, but also we use ALK system. The reason is because they are cheap. For example, we have a huge amount of storage hydrogen. We use, for example, 80% from ALK system. They can get the base. Then we use PEM system to match the fluctuations. Yeah, that's what we are doing in our national projects at the moment. Yeah, this is the PEM system. Yeah, the main problem comes from corrosion and the high cost. This I will go to detail afterward. The AEM, the problem is the durability, as I said just now. Efficiency, yeah, basically because AEM, they are alkaline environment, they can use cheaper catalyst. Yeah, but in reality at the moment, they are not cheap as we think. And also because this membrane, the conduction, for example, as a proton exchange membrane, the conductivity is quite good. But for this membrane, the conductivity for OH is not as good as the proton exchange membrane. So here we have a higher ohmic resistance. Yeah. But the structure, they are really similar. Okay, for SOEC, yeah, as I said, the only thing is high temperature and safety issues. Yeah, then we go, my focus is to the PEM system. Yeah, with the PEM system, at the moment, for example, yeah, I will try to go one by one. For example, first we talk about the catalyst. For the catalyst, I think a lot of researchers in the world, they developing the catalyst, but in the end, they found at the moment, the best is iridium for the anode side for catalyst. For example, for the oxygen OER reactions. And for HER, they use platinum with carbon materials. Yeah, and this more or less they consider standard as today. Yeah, and but how to develop this? They try to get the high activation, good durability, low cost. How to, based on this material, people doing a lot of research. But for example, the first one is try to develop this to do the size optimization. For example, we can reduce the size of the catalyst. You can get a better effect. That's someone working on it. And also, we try to develop a structure design. For example, we can change the electrode structures, and also we treat the surface wettabilities. We can find good results. And the last one is try to make the metal dopings. Yeah, with the other element doping into the iridium. They get a good result and reduce the application use of the iridium. Yeah. The next part is the membrane. For the membrane, at the moment, still people use nepheum from Dubon. Yeah, this nepheum is since a long time regarded the best membrane material for fuel cells. And nowadays, we also use this for water electrolyzers for the system. Yeah, but the people can. I've checked a lot of publications. Most of the people working on nepheum is for fuel cells. For water electrolyzer, for recent years, increasing. Yeah, but still less than for fuel cells. But for myself, I believe they have a difference. Even the same membrane, when they use for fuel cells and for electrolyzers, they are very different. The reason is, for example, for the fuel cells, we have the oxygen phase and hydrogen phase to produce water. And before the running, we need to humidify the hydrogen to put the vapor phase into the hydrogen. That means the reaction is more in gas phase. we use a little bit water or the vapor. But for the electrolyzers, we use liquid water. And the whole system is a bit different because the liquid water is a continuous phase, and the bubbles is a dispersed phase, is different. And because of this, we have heard this, the Shirotok's paradox. That means normally we believe when the relative humidity equal to 1, then we have the good same swelling rate as the liquid water. Yeah, normally from thermodynamics it's the same. But in reality, we've did a lot of tests, they are quite different. For the liquid water, they get much higher swelling rate than the RH equal to 100. Yeah, but in reality, we have this. People believe this may be due to the history of the thermodynamics. Yeah, but anyway, they are very different. That makes the naphthalene itself swelling rate is very different. Yeah, so in the end, we have a different behavior for this part. Yeah. And also here, I don't know if you could recognize this here. For example, here, we put it vertically, 90 degrees, then we have here. This is membrane, this is catalyst layer, then here is we have this PTL layers. Then we can see this proton go from this side, from the membrane to the, proton, they go through the membrane, but here we have the electrons. The electrons, then we go back from the PTL. Then also, for the water goes in and oxygen going out. Yeah. Then we can see this transport of the water and the transport of oxygen, they are opposite. The one goes in, the other one is going out. Yeah. Yes, for the system, that means we have it's difficult to do the transport because water, oxygen, they are really in opposite direction. And also, for the PTL, we have a border on it. Then the border we use for the conduction of the electrons. And of the space, we use the transport of the water and the oxygen. So the system is quite complicated. Yeah. And if we have this metal here, then after a few running cycles, then here we will have some of these passive layers, then it makes the detachment from the layers. For example, if we have the full passive layers, then the catalyst will completely gone. So that means we need to take method to control the corrosion rate. Otherwise, the system failed. Yeah. And here, in this papers, we can see here, this is a catalyst. And here is the wall from the PTL. For example, if we have a large space compared to a small space, then we have electron conductivity because electron need to be conducted into these catalyst layers. But catalyst itself is not a good material for the electron conductions. That means we need to sort this space. For example, the smaller is better, yes, and the large is not good. Yeah, but the problem is if the space is too small, we will have problem for the oxygen transport and also for the water two-phase flow. Yeah. Then another issue is, for example, if this is too small, the P-polar plate can cover this PTL area. The water cannot go in and the gas cannot go out. Yeah. So we have a lot of issues with mass transport problem. Yeah. But when we come to this bipolar plate and PTL, we can see they are one of the most important components in the system. The reason is they take up 70% of the cost. Yeah, because they are more expensive than the MEA system. Yeah. So how to reduce the cost of BPP and PTL becomes a major concern for today. Yeah. For example, another thing. Sorry, I forgot. I don't know how much time I have. Sorry, I will try to make it fast. So for the whole system, before we're working, for example, for the electrolyzers, we get the membrane, then we put the catalyst. Yeah. Then we put the PTL at the bipolar plate. Okay, then we have the stack. But afterwards, people think, yeah, if we want to reduce the cost, we have this balance of the plant. We have one stack, the balance plant is comparable. But if we have 2 stacks, then we need twice the balance of the plant. If we have 3 stacks, the balance plant, we need again a lot. So then we think, if we make 1 stack bigger, then we reduce the cost for the balance of the plant. Yeah, that's why today we try to make this electrolyzer bigger and bigger. In China at the moment, for the alkaline, we can get 2,000 cubic meter per hour. Yeah, really big. then we can have reduce the cost of the balance of the plant. For the PEMWE, we do the same. Yeah. But if before we have a smaller one, we don't have a real problem for the two-phase flow transport problem. But today, if we make it very big, then we have the unevenly distributed current, then you have unevenly distributed heat, then we have unevenly distributed two-phase flow. We create a lot of problem. We're coming up with hot spot, and it has influence to the lifetime of the PEM systems. Yeah. So that's why today it's very important to develop a system to have good transport for the oxygen and the water. Yeah. Yeah, this for the flow fields. This is, I think, this experiment was made with neutron radiations. For example, we can see here, the red area response is gas, and here blue area is for the water. And here we have a high density. We can see a lot of gas accumulated here. They cannot be timely evacuated. Yeah. And also for the PTL, we have the same. We have a low density, it's okay, it's blue, but we have high density, we can see close to the catalyst, we have a very thick layer of the bubbles. Because the bubbles cover the surface of catalyst, the water cannot come in, then the reaction stops. Yeah, so that's another issue, how we can put this bubble out. And here, normally, because we have the heavy reaction here, then we will have heat temperature. Temperature is higher. Then we have a little bit this convection. The convection effect can remove a little bit of bubble, but this effect is not evident. The reason is because you have a compact system. For the catalyst layer, normally we have the pore size about a few 100 nanometer to a few micron. But for the PTL, we have about 50 micron. But for the channels, we have 1 millimeter roughly. But for example, we have in total 1 millimeter high. Then inside, we have a different size of transport. Yeah, it's very difficult to meet all the requirements for the structures. Yes, and the second thing is to use the cheaper coatings, because normally at the moment people use platinum, and we try to replace platinum, gold, iridium to use niobium, tantalum, and titanium nitrate, for example. Yeah, so that's another method to reduce the cost. Yeah, here I go very fast for this. For example, here we have the fibers, and here we have a sintered powders. Yeah, the good thing is when we use fibers, we can put fiber together to make a felt. And for this, we have a lot of powders, then we can sinter to get a porous media. Both works, but it's very difficult to say which one is good, which one is better. It's very difficult because when we check this map, bubble map, we can see we cannot identify which one is okay. And when we check this curve, we can see, yeah, we can see here, this one with the sintered powder is better. But in my opinion, this kind of experiments you can find a lot in literature. But if you make this comparison to say which one is better, it's difficult. Because, for example, even PTL itself, you cannot identify if it's good for mass transport or not, because they need to work together with the channel system. Yeah, when they're compatible, then it's good. Yeah. Yeah, the good thing here is when we use this fiber sense things, we can tune finally the in-plane transport and the through-plane transport by ourselves. Yeah, that's also a good concept by the paper. Yeah. Then with the people studied the different gradient. Yeah, for example, with the gradient alignment, also they get some data. Yeah, but for me also the same. It's difficult to say which is good. In the end, they get something that means small pores, medium pore, large pore. They got some good results. But for example, if we have a gradient system, that means we have a lot of contact between the net. If we have a lot of contact, we will have this problem called parasitic resistance. Yeah, then we will create a lot of other problems. We have a good mass transport, but not as good as for the electron conductance. Yeah. Yeah, this is also another researcher did this work very well. For example, here they have only fibers, here only net. In the end, he put fibers net together, they get good results. The reason is when they put the fibers close to the catalyst, they have very good contact. And also put the net close to the channels, they have very good transport of the water and oxygen, for example. This is too small, it's blocked inside. This is bigger, then it's okay. Yeah. So they use this gradient, they got very good results. Yeah, these are also people working. Basically, this design before all from fuel cells, But nowadays they try to use for water electrolyzer, it works. I think they don't have something special, but here for me most interesting part is this one, interdigital, because normally for different layers, the transport all by diffuse. Due to temperature, they will have a little bit convections, but not serious. But if we use interdigited systems, that means they block the way the water has to go down and go up. That means we change the diffusion to a pressure-driven system. Yeah. Also, we have some good results. Here I go through faster. Then here in this paper, they put some elements to try to guide this bubble, how to go out. At this system, they try to separate the bubble to avoid this form the flux flow, a slug flow. Right. And the last work here, in my opinion, they did very good work. This is from Fraunhofer Institute in Germany. For example, people always think we how to develop channels, but in the end, they did one test. This is with channels, the other one is no channels. They have only different layers. In systems, they have no channels. But in the end, they found very good results. For example, unless for the bubble resistance or this over potential, this one is not as good as this one. For the rest, they are all similar. But for example, the bubble resistance, if we have over than 3 ampere per square centimeter, then you have this evident difference. When you have a low current, then it doesn't matter. That means if we want to try to reduce the cost, we don't need the channels. We just put different layers and put the plate, then it works for low current density. I think this work is a brilliant work. Yeah. Yes, this is something we developed in our group. Yeah. Yeah, I go fast here. Then here another one, we try to develop the PTL. The PTL, we try to multi-angle. For example, this is the commercialized system. Here you have a lot of dead zones. The water cannot get in, cannot go out. And also they trap the oxygens inside. And here we have this structured design, then we have very good results in the end. Yeah. Because when the water, oxygen go out, they can go from this go up, from all the way out, they have no bottleneck. Yeah, that's why we can get a good result. Yeah, for example, when we're making the test, this one is from the commercialized PTL. This is our PTL. We can see this represents the resistance due to mass transport. Yeah, for all the oriented PTL, we don't have this. And for the commercialized, they have this one, very heavy problem. Yeah. Yeah, this I go then. Then the last is about the coating. Coatings also, we try to replace the gold and the platinum with niobium, titanium, and titanium nitrate. Yeah, this I will go fast. The first we developed this HEA system, it's a high entropy alloy, the system. Yeah, our work, we can get, for the potential, we can get the good range and the low count density. Yeah. Yeah, this here we use technique magnetron sputtering. Yeah. For example, in our lab, we have a lab scale test. This is for smaller one. And also to our collaboration companies, we have the pilot scale test. Yeah, we have already industrialized. And also in the CAS, in Shenzhen, our collaborators, they have very big chambers. They can have this, I think, almost 1 meter wide. The system, we can have this sputtering to cover the surface. Yes, there's some results. I go fast. Yes, in the end, we have a good effect. It's a high entropy effect dominates the formation of amorph structure. That these amorph structures can resist to the corrosions. Yeah. And another one we developed is electrophoretic deposition, the EPD technology. This technology is not a new technology. People use it for a long time. Yeah. But the problem is, normally produced by this technique is not stable on the surface. Then we try to optimize this technique. Then we get very, very stable coating layers on the surface. And here we use ITO. Normally, this indium is also expensive metal. But here the good thing is we take this ITO from the PV panels. Yeah, it's a waste for us. And we reuse the waste to the system. Because we use this system, we can do it in the beaker for lab. But in the end, for industrialized, we can use a big container. That means we don't have problem over the space. We can make a big structures, anything, no problem. And also, for example, for PTL, we have inner structures. If we use sputtering, it's difficult to cover the inner surface. But if we use this technology, we can cover the inner surface, no problem. So that's the second technology we did. Yeah, also we did good results. Yes, I go faster. Yeah, appendix, I go maybe just for the soft development. It's for the application of the hydrogen. I will go directly to the interesting part. Yes. Yeah, because soft system, normally people can produce it with FT, yeah, fish-tropic reactions, but this is a high exothermic reactions. That means normally people working on the system, we need to dilute the catalyst. Otherwise, we will have to have too much heat. This can damage the catalyst and also the system. That's we try to reduce the kinetics. But if we use microreactors, we have the possibility of without using these diluters. Yeah. So we have a really high kinetics and also very good temperature control for the system. So that's what we are working on. This system was developed at Karlsruhe Institute of Technology. And this institute, they was the first one in the world who invented these microreactors. Yeah. Yeah. Also, this Dr. Sun, he worked in the institute. Yeah, almost the same time as me. At the moment, he's also working in my group. Yeah. So, and the last slide is coming from Shuangya S SAF project. They produce 100,000 tons SAF per year. At the moment, I think this is the largest in China, maybe largest in the world. Yeah, with this FT process. Yeah, and the last year they just started, and this is funded by this China Power Engineering Consulting Group. Then also part-timely, also I work in this, in this group. We have a research center over here. So now we try to, we'll build some system for this big project. Yeah. Okay, sorry. So I have a problem. Thank you very much. And also this is some funding that partners. Okay, thank you. Okay.
Thank you, Professor Yongli. Fantastic presentation. If you have questions, se vocês quiserem fazer perguntas em português ou em inglês, eu posso passar o microfone.
Thank you.
Hi, Professor. First of all, thank you for your presentation. It was very clarifying for me. And I just have a question. I would like to know more of how do you prepare the coating using high entropy alloys. Can you explain about
good. Very good question.
the
It's
deeping
going
of
to the details. Yes. First, we prepared the target. We prepared target because we don't use the metal separately. We prepare a target. For example, we put different metals, then we give to the company. We choose different metals. They will form a target. Then we take this target directly to the machine. That means for the sputtering is once ready.
Oh, I get
Yeah,
it.
but not one by one. Okay.
Yeah, because this is a very complex process, and
Yes,
that's
exactly.
why I did the question. Thanks so much for your explanation.
Thank you.
Thank you.
Mais alguma pergunta?
Tem uma relação, você já tem uma noção do cinza para o verde?
Professor Jurandir has a question about the cost of production of conventional hydrogen compared with green hydrogen here in Brazil. Maybe today this difference is very, very high. Maybe for conventional hydrogen, maybe $1 per kilogram, and for green hydrogen, $10 per kilogram. Do you have numbers for China?
Yes, exactly same. In China, same. In China, normally, if you are a company, yourself, you don't want to buy green hydrogen, sorry, because it's too expensive. We prefer the hydrogen from the coal because it's a very mature system and also cheap. Yeah. Then we have another thing is, I know how to say English, maybe it's called coal sink something. Yeah, CO2. That means we put this CO2 emission to the market. Yeah, but for example, if your process, you save some CO2 emissions, you can sell this. then you can get the money back. Yeah, for example, that's why your green energy, green hydrogen, maybe you get some allowance from this market. Yeah, in China we started doing something like this. Yeah.
Há uma tendência que com o aumento do mercado também essa relação, essa diferença de custos vai diminuir. Então, já percebemos?
About for the future, if you expect that this production costs can decrease in China as it happens with PV and batteries.
In my opinion, sure, yes. Because I think here we have a slide. I think we have this from another report, not mine. I did it. Right here. Because by 2060, it can reach 10 yuan per kilo. Yuan is similar as here. Yeah. They say, I believe maybe not exactly this value, but I'm sure it will be reduced. Yes, yeah. Because we can see from beginning, from electric cars in China, at the beginning it was also very expensive. That the government have to pay allowance for the people who can afford the cars. But nowadays it's market behavior. Yeah, I think over years this cost will be reduced.
And now he has a electric car here.
That's very good. Good choice. Because it's yeah.
Professor, can you talk about the challenges like using resources like water, because it's a limited resource? So can you tell us
The limit over?
reserves?
Water reserves.
The amount of water needed to
Yeah.
produce hydrogen.
Okay, that's a very good question. Because at the moment, I think we didn't have much time to consider about the water, because for us, the most important is how to use this renewable energy. We don't abandon the wind energy and everything. But this is a real issue. That's why in China, we have some researchers, they're working for the electrodialysis of the seawater. Yeah, we don't take directly from the sea, then we do it. Yeah, I think we already have some demonstration in China. Yeah, I think in future, it also works. Yeah, if we use water from the fresh water, that's true. We have the limitation. But if we use water from the sea, it's not a problem at all. Yeah.
Okay, thank you, Professor.
Yeah. Yeah.
I saw that there's a few progressions and few developments in this area. That's very important over there. But I actually want to know how are related the basis, the basis research and applied science as well. How they work together, and how is made the institutional arrangements for these investments is mostly from those companies, or there's some kind of calls that they have investments from the state as well. How is made this kind of investments for projects in this area actually?
Okay, that's also a good question. Because, for example, in my institute, our university asked me to fund this institute, but the university didn't give me fundings. Then I have a close company. This company, he have a donation to my institute. Now with this donation, I bought all the basic infrastructures. Yeah, I said then with these infrastructures, then I start applying for projects in China. Yeah, so we can also get a project from the Chinese government, but normally from the government, they give you only a small fundings. But with the small fundings, I find industry partners. The industry partners, they will give me huge fundings. But myself, I have to get the funding first from government to show them I have the ability for doing this. Then industry partners, they will pay me for doing big, large projects. Yeah, like the one we did before for the national key. It's a project we have 140 million yuan. So this is a really big project in China, and that's the case. That means the government paid me a little bit, then the industry, they followed, yeah, much more. Yeah.
So the industry absorbs this technology so quickly or rapidly?
Could you show the slides?
Which one?
The one who have lab research, then the prototype, and then the industrial.
Yeah.
Where is it?
To the end? Yeah. The last one, yeah?
No. I don't know.
I think the end. Yeah?
The end? Yeah.
3 prototype.
Yeah.
Prototype, okay. Yeah, prototype, it was for the coating, I think. This?
Yeah.
Okay. Yeah.
This is the secret. I think they have the 3 steps. The basic research, then the pilot scale, then the industrial scale.
Yes. And yeah, another question you said about fundamental research and applied science. This, for example, in my group, I work on both. I work for the basic research, fundamental research, and also for applied technology. Because if I work only for the basics, then the industry, they will not pay me for working for anything. Yeah. So that's why I work for both. So in my group, the students also divided to two parts. Yeah. Someone working on fundamental research for the papers, someone working for industry, yeah, for get more funding. Yes. Yeah.
Professor, there is one question from the online audience. It's about turquoise hydrogen from pyrolysis of methane. He wants to know if you have some information about this, if China is also researching, developing this type of technology.
Yes, from methane, biomethane. Yeah. Yes, at the moment, we also produce by reforming or methane for forming hydrogen. In China, it's also a big industry, but the problem for us, that is not from bio. Yeah, because in China, the biomass is not as rich as in Brazil. Maybe here you have a lot of agriculture, you can collect a lot of biomaterials for producing biomethane, then biomethane or biomethanol to produce hydrogen. But in China, we're also doing this, but compared to here, because we don't have enough biomass, that's the problem, yes. But this technique itself is good. Yeah, we will also develop this.
Thank you.
Yeah.
Any more questions? The professor, thank you very much.
Okay.
Quanto demora? Pessoal, só queria comentar um pouquinho sobre o que ele apresentou, só para a gente depois refletir, né? E comparar o que acontece com a gente no Brasil e na China. Bom, primeiro aquela figura que a gente comentou, né? Da universidade fazendo a pesquisa básica, transformando isso em protótipo, e junto com a indústria transformando isso em produto. Esse é o diferencial da China, né? Que a gente vê chegar aqui já como produto final, mas é isso que está fazendo a China crescer tanto, né? Em termos de desenvolvimento tecnológico. E também essa busca tão completa dentro da universidade para desenvolver, por exemplo, melhores eletrolisadores, né? Trabalhando sempre na busca por materiais mais baratos, que possam ter maior durabilidade. Vocês que são da área aí poderiam até explicar melhor, né? Mas, por exemplo, tentando utilizar materiais mais baratos, tentando proteger esses materiais contra a corrosão para que a durabilidade do equipamento seja maior, tentando facilitar o fluxo de água dentro do equipamento, o fluxo de bolhas de oxigênio, de hidrogênio. Então, é uma pesquisa muito ampla que busca melhorar todos os componentes, né? E, ao mesmo tempo, também diminuir o custo. Então, eu achei muito interessante, apesar de não ser a minha área, foi isso que eu entendi. Se tiver alguém aqui que queira comentar alguma coisa mais sobre isso? Não? Tá. Então, você já botou o vídeo já? A Cláudia da Chamando Energy, ela me pediu para fazer uma apresentação da cooperação, da parceria que a Unicamp e a Chamando. Então, a gente está implementando aqui na Unicamp. Numa primeira fase, não envolve a produção de hidrogênio, mas na segunda fase, sim, a gente vai ter a produção de hidrogênio verde. Claudia, I'll present to them a little bit about our experimental farm.
I should understand.
Now she can speak Portuguese a little bit.
Muito bom. Eu falo muito mais.
Então, pessoal, com a Chamano, a gente está implementando aqui na Unicamp isso que a gente está chamando de fazenda experimental agrovoltaica, que vai ser implementado aqui no nosso RIDS, né, que é o Hub Internacional para o Desenvolvimento Sustentável da Unicamp, que é o projeto de utilização da fazenda argentina, a fazenda que a Unicamp comprou recentemente, para fazer parcerias e centros de pesquisa na área de sustentabilidade, não somente energia, mas todos os aspectos envolvendo desenvolvimento sustentável, né? E dentro dessa fazenda argentina, um dos primeiros projetos vai ser a implementação de uma fazenda experimental agrovoltaica. E a Unicamp vai fazer isso em parceria com a Chamano Energy, que também faz parte dessa cooperação Unicamp, Chamano e a Universidade NCEPO, lá da China. Então, é uma fazenda agrovoltaica, ela combina a produção de energia solar e, no mesmo espaço, a produção de alimentos. Então, a gente combina o agro com a energia, né? E nesse projeto nosso também, a gente está incluindo ainda, a Dulce que perguntou sobre a água, que também é um outro grande problema que a gente enfrenta, né? Então, a gente vai, nessa fazenda experimental também, fazer coleta de água de chuva. Então, a gente vai ter aqui produção de energia, produção de alimentos e utilizando água recuperada da chuva para fazer o sistema de irrigação. Então, a gente entra no que a gente chama de nexus água, energia e alimentos, onde você tenta otimizar todo esse processo de forma integrada. E esse é um projeto na Fazenda Argentina que a gente chama de Hub de Energia Sustentável. Isso, a Fazenda Experimental, é a primeira fase desse projeto. Numa segunda fase, a gente vai entrar na produção de hidrogênio verde, amônia, que vocês viram aqui, biogás, biometano, na segunda fase. E numa terceira fase, a gente vai trabalhar também com a produção de SAF. SAF é combustível sustentável para a aviação, né? É querosene sintético, querosene sustentável para substituir o querosene fóssil nos aviões. Você pode produzir isso, ele mostrou aqui, através dessa reação de Fischer-Tropsch, né, que você usa hidrogênio e você consegue produzir esses combustíveis sintéticos. Então, um projeto de 3 fases. Isso aqui é a primeira fase do projeto. Então, o que é que a gente vai ter nessa fazenda? É uma parte da fazenda argentina, que vocês podem ver aqui, vai ser do lado ali do Museu de Ciências, aqui é na fronteira no final do nosso campus, que faz fronteira com a Fazenda Argentina, a gente vai ter uma área de 10 hectares para fazer esse hub de energia sustentável. Então, nessa fazenda agrovoltaica, a gente vai ter 3 áreas, uma área com 70% de sombreamento, uma área com 30% de sombreamento e uma área sem sombreamento. Nós vamos plantar tudo quanto é coisa aí possível nessas 3 áreas para descobrir o que tipo de planta que vai bem com sombra de 30%, com sombra de 70%. Então, vocês sabem que aqui no Brasil já tem bastante produção em área sombreada, né? Sobra sol, né? Às vezes para a planta isso é ruim. Então dá para fazer essa combinação, só que a gente tem que fazer essa pesquisa para descobrir o que vai bem em cada nível de sombreamento. Então, por isso que a gente tem esses 3 tipos de área, né? Aqui uma área sem sombra para você comparar como a planta se desenvolve em pleno sol e na sombra. Também a gente vai ter metade da usina com trackers, com painéis móveis, porque se você tem pouco sol, você pode priorizar a planta, deixar aquele sol para a planta e não gerar energia naquele momento. Quando você tem muito sol, você pode priorizar a geração de energia e mandar ainda para a planta a quantidade de luz que ela precisa, né? Então, é metade com trackers, metade sem, para a gente comparar também o efeito disso nas culturas. Como eu falei, também com coleta de água de chuva. E também, então aqui é a área com 30% de sombreamento, aqui uma área sem sombreamento, né? Isso tudo somando 10 hectares. Ali vocês estão vendo os tanques de armazenamento de água de chuva. 2 milhões de litros de água de chuva a gente vai conseguir captar nessa usina que vai ser de 5 megawatts. Então vai ser possível a gente captar 2 milhões de litros de água de chuva nessa usina, nessa fazenda experimental. Vocês estão vendo também que ela vai ter ali, aqui a área sem sombreamento, né? Ela vai ser uma fazenda, então, que a gente vai coletar água nos painéis, e ela vai ser equipada também com uma quantidade enorme de sensores. Sensores de tudo quanto é coisa. Então, vai ser uma fazenda inteligente, 4.0. Uma indústria 4.0. Então, vai ter também IoT, sistemas de sensores para coletar dados no ar, dentro da terra também tem sensores para a gente otimizar a irrigação e a fertilização. Então, vai ser tudo otimizado. Sistemas de luz complementar também, já que a gente tem um montão de energia durante o dia, a gente vai poder usar a energia para fazer a planta continuar crescendo durante a noite. Tem plantas que precisam de muitas horas de luz. Então, aqui a gente vai ter também a infraestrutura para estudar esse tipo de planta, né? Então, o uso de sensores para você otimizar toda a irrigação e também a fertilização da fazenda, né, em todas aquelas áreas, inclusive a área sem sombreamento. Então, e inteligência artificial para otimizar todo esse processo. Então, ela vai ser uma fazenda inteligente, né? Tudo isso vai integrar, eu esqueci de mostrar para vocês, ela vai ter aqui um centro de operações da fazenda inteligente. Tem um predinho ali onde você tem o centro de monitoramento, os servidores que vão ficar rodando inteligência artificial para você conseguir otimizar todo esse processo. Então, a gente já tem um acordo com a Chamano para implantar essa fazenda. No momento, a gente está tentando vencer as nossas velhas dificuldades jurídicas para parcerias público-privadas que a gente tem no Brasil, porque a metade do recurso para essa fazenda experimental é da Unicamp, metade é da Chamano. Isso aqui vai gerar um espaço de pesquisa para diversas faculdades da Unicamp, por exemplo, na área agrícola, na área de computação, na área de engenharia elétrica, na área de gestão de recursos hídricos. Então, vai ser um grande equipamento de pesquisa que a Unicamp vai fazer. E mais ainda, o nosso combinado aqui com a reitoria, com a Unicamp, é que a metade da energia dessa fazenda vai ser para a gente fazer projetos em outros desafios de transição energética, por exemplo, a produção de hidrogênio verde, a produção de amônia, a produção de SAF. Então, a gente vai ter dessa usina energia para futuros projetos, que eu falei que seria aquela fase 2 e a fase 3 que a gente quer fazer. Depois disso, a gente vai ter hidrogênio no campus, então a gente vai poder ter ônibus a hidrogênio também. A gente vai ter biometano no campus, então pode ter ônibus a biometano, então o campus também vai ser um laboratório vivo de mobilidade urbana de baixa emissão. Então, um roadmap de projetos aí para os próximos 10 anos, onde essa fazenda experimental seria um primeiro passo, que já está muito perto de ser concretizado em parceria com a Chamano Energy, aqui presente com a gente hoje. E com grande participação da Enicepo também. Tem várias outras tecnologias que a gente já está discutindo para colocar nessa fazenda. Vai ser uma coisa única, aqui no Brasil, na América Latina e Caribe, não vai ter nada parecido. E o principal objetivo é gerar conhecimento sobre essa integração entre a produção de alimentos, produção de energia, com o uso otimizado dos recursos hídricos, integrando sensores, inteligência artificial, etc. Vai ter pesquisa aqui para quem estuda planta, para quem estuda energia, para quem estuda água, para quem estuda computação, né? Tudo isso é o que a gente está desenhando aí para os próximos 10 anos aqui na Unicamp. Claudio. Thank you. Would you like to say a few words? Could be in Portuguese.
You follow Portuguese multiple, mas English is better. Yes, we are very proud here to have the opportunity to jointly invest this agriculture solar integrated system, because our company has a lot of experience in the consolidation for the technology, and also we're very interested in this area because it could be a demonstration for the Chinese technology, for our company's technology in terms of hydrogen, and also we could produce hydrogen into ammonia to be used in the irrigation system, because as we know that now Brazil need to import 85% of the ammonia from Russia, from Ukraine, but it will be more important to produce locally. And as well for the SAF, which is for the diesel for the like airplane, it is also mandatory to use SAF in the future to in these airplanes. So I think Brazil has a very good resources, natural resources, renewable energy. In Brazilian people are very intelligent. It's totally like possible to produce in Brazil, to make Brazil a very strong and independent country. Thank you so much.
Thank you, Claudio. Então, acho que foi isso, pessoal. Não sei que vocês têm algum comentário, alguma pergunta a mais para Cláudio, professor, ou para mim também.
Thank you very much, first of all, for explanation. Could you share some information about how your company pretend to produce ammonia, green ammonia?
Thank you. So for the hydrogen to ammonia, I think it is previously in China, for hydrogen to ammonia, it needs a very big investment, usually like 100,000 ton to 300,000 ton production. But this is not very fit into a scenario of Brazilian local situation, because in Brazil the transportation is very expensive. That because so far the train system is not very mature. So our company, together with our engineering and our professors, we develop like a tailor-made smaller equipment with a consolidated solution with hydrogen, put into hydrogen together with nitrogen from the gas to consolidate it into liquid ammonia. And you need to, of course, you have to add some additive to make it stable. And you need to have the irrigation system for or some cars. You jump the liquid ammonia was diluted like 12% to 20% into the earth to avoid it escape from the surface, so that we tailor-made this solution that you could only produce like 3,000 ton per year for this, or even 100 ton per year. For this equipment, I think it could be transported to each farm. So for these farms, they're located probably in Goiás, in Minas Gerais, so that they could use for these farms. No need to like transport the ureas and ammonias from the port. So this is actually tailor-made for Brazilian market and customers. We have now one like a trial project with also a listed company. Also, it's a like a sugar cane company. They export to US and export the sugar, the organic sugar to China, so that they are doing the testing how to utilize it, utilize the liquid ammonia in their plant, because they used to use liquid ammonia, but after the fertilizer company and the Petrobras was sold to another European company, that company was shut up in Brazil, so that they could only buy urea from the port. But so they're very happy that the product come back to Brazil, so that they're testing it in their agriculture plant so far. Yes, thank you so much.
Mais alguém? Não? Muito bem. Então, a Raquel está convidando a gente para tomar um café aqui fora, né? É? É um cafezinho aí que ela conseguiu de emergência.
Oh, very good. Thank you very much. Yes.